Hey everybody. So this is a unique video. I found this method called torque clustering, and just to give you an FYI, so I found this. This research paper is called Autonomous Clustering by Fast Find of Mass and Distance Peaks, and the GitHub for this. So they have the GitHub available, and the GitHub is like a whole bunch of code, a ton of code, and then this paper is locked behind a paywall. So. I was very interested in exploring this method, and then so very flat out, essentially what I do in instances like this where I hit a paywall is I'll feed this particular research paper to LLM models like ChatGPT, Gemini, etc. And just flat out, I mean, I know for a fact that they're scraping this data like it's their job, and that they can access this data if they have access to search, right? They can access this IEEE database, whereas I have to pay as a human. And then so I just essentially, I have GPT and Gemini search this paper, and then I have them come to a consensus and do some work as to kind of like what this framework should look like. Give me some ideas, and then I explore that up front, right? So this first implementation was my first go at this, how to reconstruct essentially what they did, and then I found more research around their method. I found their GitHub, and then I was able to pull it together. And then by the end, I think I have a good, faithful reconstruction of their method here. And it's a pretty unique method. So diving into it very specifically, this notebook provides a comprehensive demonstration of torque clustering, which is a physics-inspired clustering algorithm where data points are treated like particles that exert forces on each other. This is very gravity-based, extremely gravity-based. It's really cool. The magnitude of these forces depends on each point's mass and distance to its neighbors. The key steps can be summarized as follows. 1. Mass calculation. Several methods are showcased to assign masses to data points. So each data point structure gets a mass assigned to it based off of uniform. So every point has the same mass. Density. Mass is proportional to the local density using k nearest neighbors. Feature sum. Mass is proportional to the sum of a point's absolute feature values. Feature variance. Mass is proportional to the variance of a point's features. This flexibility allows notions of importance for each data point. So more important data points have more mass, obviously. And then torque force computation. So you compute pairwise distances are computed via some calculations, and then a net force of torque is calculated for each point, summing contributions from all of the k nearest neighbors. Points with higher masses pull more strongly, and points far away pull more weakly, so often inversely proportional to distance or its square. So the gravity of the data set is proportional to how strong the signal is in the data set in this instance, right? It's really cool how this breaks down. So position updates and convergence. Each point is iteratively shifted in the direction of its net torque scaled by a learning rate. Updates stop when the average movement of points is below a specified tolerance or the max number of iterations is reached. Clustering and evaluation. After convergence, either a simple rule nearest neighbors or removal of abnormal connections is used to partition the points. Or alternatively, you can see in the last one, I use k-means and k-nearest neighbors to the final torque adjusted positions. And the notebook uses metrics such as adjusted rand index, ARI, and normalized mutual information, NMI, to evaluate performance against known ground truth labels. Bottom line here, this is an unsupervised training method, no labels whatsoever. We're giving it, and in this instance, I'm generating synthetic data, not giving the model labels. It's 100% unsupervised. And the model is training itself off of this gravity method. Essentially, it works. I'll show you at the end. We get very near to 100% accuracy. So overall, this notebook is a self-contained exploration of torque clustering, demonstrating how different mass assignments and parameters can affect cluster formation. It includes code examples, performance evaluations, and visualizations, making it a practical resource for understanding and experimenting with this unique clustering technique. Hope you like it. You won't find it anywhere else. That isn't buried behind paywalls at the moment. They did say that they open source the code, so this is my open source iteration on their code. And then so very first thing, right, is this is my first iteration of it, and then understanding this gravity, data as gravity. Right? That's what boggles me. I'm like, okay, this is cool, right? So I build this out independent of the paper, and then so I build out uniform, density, feature sum, feature variance, And then I perform like different calculations, I throw the board at the clustering calculations essentially, right? And then I just perform a whole bunch of clustering calculations. So I cluster based off of uniform mass, density, features, and feature variance, and then just go through and I get something like this: a cool visualization and a very simplified version of this method. Okay, so this method works. Like this gravity-based method does something, right? I can get data out of it. Cool, and then I can see this clustering, how it works, and it looks pretty cool. And then so I go through and then I do more math here, right? And then so I essentially update based off of the research papers. And then it's in the research, very specifically, I find out that they're utilizing Euclidean distance very specifically, and they're utilizing Euclidean matrices. Euclidean distance matrices is a large portion of this. And then a lot of people, it's a lot of debate, right? Like to me, there's different spaces and different mathematical spaces, and they each have different properties. So I've talked about this before on my channel numerous times: Euclidean, hyperbolic, fractal spaces, etc. Right? And then I don't think that there's one space is necessarily better than the other. If you're mapping the universe, then you don't want to use the Euclidean space because the universe isn't Euclidean overall. But if you want to get a perfect iteration, like a space where it's 100% the variance and everything is going to play according to the rules. A triangle is going to have three sides that all equal out to 180 degrees, etc. Euclidean space is very good for that, and like there's no reason to like just exclude and poo-poo Euclidean space over like as a 100% space just because it doesn't mathematically represent the universe to me. And then so I think like a lot of people at this moment, like going through kind of like that transition in that phase where a lot of people are recognizing like, oh, hyperbolic space is actually kind of unique and it's got like all of these unique properties, and then a lot of people just want to throw out Euclidean space once that happens. But Euclidean space has value too. And then so in this instance, what it allows us to do, and especially when we're dealing with these distance metrics, right? And I run into this a lot with hyperbolic space, just because there's a lot of issues when you measure in hyperbolic space, especially when you get near the edges, right? And then you don't run into those same issues with Euclidean space. It allows you to measure distance very accurately. And so in this instance, what you can see is we have essentially, my first test is to utilize this clustering to try to generate labels and based off of it, and I'm able to, right? So it's an unsupervised learning method without labels, but the model has to be able to generate its own labels. And then so that's the first step here, and we can see that it does it. And then so this clustering method, purely based off of mass measuring, so mass mathematical calculations, torque clustering allows us to essentially generate labels. And then from there, the next step that I do is build a trainer, right? So I build out the model and then build out a full trainer and a training and evaluation process, create a full synthetic data process for it. So here's my synthetic data. I'm generating the clusters for it. In this instance, I'm training it again on those same metrics. So at this point, I have a good understanding of how the research paper is working. So I train it off of uniform mass, density mass, feature sum mass, feature variance mass, uniform mass, and I run multiple tests for each one of these and based off of different torque thresholds. And we get the labels. The model is producing the labels as a result out of this itself. So it's a lot of just mathematical calculations, right? And then my first test here, these results, this is like not good. Yeah. I want these to be like 1. Like if these were 1 uniform across the board, that'll be that, right? It'll be like exactly where we want it to be. But we see a lot of zeros on the left-hand side, and then the highest that we get on the right-hand side is 0.42. So very far away from 1. And then when we look at our tests, these confirm, right? We want these to be more into groups. So we want these to look more like our ground truth, and none of these look like truth, right? And then so I go through and then just essentially like clean things up. The biggest thing that I do, like the biggest thing I do is add k nearest neighbors at the end of this. So k nearest neighbors for the end clustering, right? So these algorithms, they're all clustering, and it's the the torque clustering algorithm as far as I understand it. But at the end, I just add this like k nearest neighbors clustering on top of it. And then so I'm assuming that they're going to do this in their research as well. And I'm assuming I just missed it in my first go through, because once I add that, just by like basically that simple calculation, I get ones across the board. And then we can see here, we'll go through the different iterations and then our end result for comparison. To 100 is exactly what we want it to be, right? So here's our ground truth, and then here's our comparison, and then it's much cleaner, right? It looks exactly like the ground truth, as opposed to all of those mixed examples. And then so very straightforward. This torque clustering algorithm is super cool, works really well. As far as I know, it's the code exists on GitHub, but it's really hard to get it together. So this is the simplest implementation that you're going to find outside of their official release, and the paper is hard to get access to. So here you go, torque clustering. I think a lot more people are going to be talking about this hopefully soon, because this seems really cool. But if you like this type of content, please like, subscribe. Thank you very much.